Welcome. This is the second video in the series on quality assurance. In this video, we will look at several tests that are performed on the X-ray equipment. Also, we'll have an introduction to the testing equipment used and how it's utilized. If you haven't watched the first video on quality assurance, I recommend you do it at this time. Let's get started by talking about testing guidelines. Guidelines for testing and parameters for acceptable performance have been developed for all types of medical imaging equipment, digital processing equipment, and image display equipment by the American Association of Physicists in Medicine, which is made up of medical physicists. A medical physicist is someone who develops and maintains quality assurance programs to ensure high quality imaging in radiology. When we say physicist, it's referring to a medical physicist. And this is our symbol here. In this video, we won't be talking about image display equipment, any testing or parameters for that. In the fifth video of this series, we will cover that topic. When an exposure is taken using a fixed technique, there is KVP that we set, mass that is set, and the distance are the three primary factors that we can control. And of course, mass, as we learned, has two components, MA and time. The exposure timer controls how long the X-rays will be created for during the exposure, so how long the exposure will go on. There are several ways to check the accuracy of the exposure timer. Most commonly, the radiation physicist uses an electronic ion chamber or photodiode device, which can be seen on the right. So this is the ion chamber right here that would be exposed, and then the readout panel. The timer should be checked whenever a major repair or part replacement has been made. The acceptability is plus or minus 5%. Times less than 10 milliseconds are allowed a wider range. This is because it's difficult for very short times for electronics and for electrical equipment to manage that very short time. So it has a larger range of acceptance than the 5%. But all the times above that are plus or minus 5% of the time it should be. MA linearity. So we talked about the time component of mass, which is the S, seconds. Now we're going to talk about the MA component. With all other factors equal, changes in MA should result in a directly proportional change in the exposure. So if we go from 100 MA with the other factors set, and we keep all those other factors the same, and we go to 200 MA, we should expect doubling the amount of X-rays produced. There's going to be twice as many electrons that are boiled off, twice as many X-rays that are produced, and then the exposure should be doubled. If you need a review on any of this, I recommend going to the playlist labeled Principles of Radiographic Exposure 1. Various factors including statistical variations in generator, incoming electricity, and wear and aging equipment can cause inconsistencies in the actual MA output. So all these things can change what is expected. Collectively, these factors are more difficult to control than those affecting the exposure time. The exposure time's it's just a circuit, it's just a timer that is set, and it keeps the electricity flowing, keeps the electrons flowing in the tube at the cathode for so long, and then it can shut off, and that can be very accurate. The MA has wider fluctuations due to these factors that we talked about above. So plus or minus 10% for each adjacent station is acceptable. So we'll test one station, we'll measure that exposure, whatever it happens to be, when a physicist or engineer or a QA tech would do it, they probably have one that they start out with. Maybe they always start with 150, whatever it happens to be, and that's kind of like their baseline exposure, and then they'll go up by doubling. Then they'll go up by doubling. Then they'll go up by doubling. Each one should be within 10% of what is expected, which would be twice as much than within 10%. We'll see how we calculate that on the next slide. So again, the most accurate way to measure MA is to use an ion chamber and to calculate the microgray divided by mass obtained at each MA station. A 100 MA to a 200 MA exposure, the result should be doubled within a plus or minus 10%. We can see the graph here to the right that the blue line is perfect linearity. So as this goes up by 1, and as it doubles from, if this is 1, this is 2, if it doubles to 4 here, on the y-axis is also going to correspond to the same amount increase. So so from 2 to 3 on this axis is going to go from 2 to 3. It's going to increase the same. That's perfect linearity. The green area here is the acceptable variation for this test, which is plus or minus 10%. So we say that any point, if we were testing the points in platinum along here, any point in here would be an acceptable variation. The red line, if this was the data that we were collecting, this would be unacceptable, because at any point, if it falls out of the green, it's no longer an acceptable test. We would have to repair something. Something would have to be reinstalled, something would have to be recalibrated, and the equipment wouldn't be able to be used until it fell into these parameters. Let's go ahead and do an example. If 100 MA exposure is measured at 22 micrograys, let's say, if the time is 50 milliseconds that's being used, then the microgray divided by the mass, 100 MA, 50 milliseconds, is 4.4 is the value that we get for this. Now, with all other factors remaining the same, what is the acceptable range when 200 MA is used? Take a quick second, pause the video here. You can try to work this out. We would expect that the exposure to double so 44 micrograys is what we would expect to read on here. Within the plus minus 10% is what we need the acceptable range to be for the question. So we need, with the calculation, we need it to be within 3.96 to 4.84 for the values. If we did get 44, that's perfect linearity. As we talked about before, it doubled. We doubled here, and we doubled on the Y, on the output. So we put that in the calculation, and we would get 4.4 with the 200 value, the 44 here. We'd get 4.4 again. So we can see that this calculation here, the reason that it's used is because it's going to give us the same exact number if it is accurate. If it is doubling like it should, it's going to be the same number every single time. So we can easily see, once we get a baseline, that this is our acceptable range. And if this was our values, and if anything fell out of this, then it would be easy to spot, because we're standardizing the measurements here, okay, with this calculation. That's why they use it. Let's move on, and we'll talk about exposure reproducibility. So far we've talked about the MA, the linearity of each MA station, and we also talked about the exposure timer, the second. So we talked about mass. Now we're going to talk about the reproducibility, which is the ability to repeat the same overall technique settings and to obtain the same resulting exposure. So what if we take an exposure at 70 kVp and 50 mass? Then we take another one at 70 kVp and 50 mass. The same output should be resulting. Okay, so what if we do this 10 times? And that's actually how we test it. We test 10 identical exposures are made. The average of those exposures is found. then each individual reading is compared with the average. Okay, so we find the average of the 10, then we compare each of the readings with the 10. A plus or minus margin of 5% is the acceptable range on this test. For exposure reproducibility, the equation used is very similar, or has the similarities, if we notice, to the MA reproducibility, or linearity, MA linearity. The similarity is right here. Micrograys divided by mass. That's the same exact value we found in the last test in the MA linearity. So we take the exposure tested, okay, then versus the average. So we find the average of the 10. We just add them up, divide by 10. That will be the average here, this value. Then we find, then we divide it by the average exposure. Okay, so the average, and we take the exposure tested. So we're finding the difference here, and then we're just dividing it by the average. Okay, and that should be within 5%. Okay. All this can be a little confusing, so let's go ahead and let's just look at an example using the equation of exposure reproducibility. We take 10 exposures with the same exact technique. The ion chamber readouts we say are these below: 8.2, 7.6, all the way to 8.4 milligrays. The mass that we used was 100 MA at 1 second, so 100 mass. The average chamber readout is 8.1 milligrays. So 8.1 milligrays divided by the 100 MA times 1 second equals 81 micrograys. We got that 81 micrograys. If you're trying to do this calculation, or you're trying to work out how it got here, because this is a micrograys and this was in milligrays. Okay, so it's 81 micrograys here. Then test each exposure. So the first one is 82 micrograys with micrograys mass minus 81, which was the average from the equation before, divided by the 81. This equals 0.012, which is 1.2%, which is within the limits. Our limits were plus or minus 5%. Okay, so this was over by 1.2% of the average. Continue with each ion chamber readout, and we find that all of these other ones are in compliance, but the 7.6 is not. The second exposure of 7.6 is negative, so plus or minus, but the negative 6.17, so it's beyond the negative 5%. So the equipment is out of compliance. We would need to go back, engineer, physicist, the QA tech, whatever they could do, they would do some kind of recalibration of the equipment before it could be used. The next test is the half value layer. The most important quality of the X-ray beam is to penetrate through the body. That's why we use X-rays instead of light or anything else, because X-rays have the energy to penetrate through the body, expose the CR or the imaging plate or the film, possibly even behind it, and create that image. That is our purpose. Beam penetration may be raised in two ways, so we can raise up the beam penetration in two ways. One of them we should know, and the other one is by increasing minimum energies in the beam by adding filtration. So if we add filtration, it hardens the beam, we would say. So the average energy of the beam is going to go up. Okay, so the penetration of the beam is going to be higher overall when we add filtration. By increasing maximum energy in the beam by raising kVp, so we can just increase the maximum energy of the beam by raising the kVp at the console. So those are the two ways that we can increase beam penetration. Both of these raises the average energy of the beam. The only true measurement of X-ray beam penetration is the half value layer. Half value layer. So to test this, an exposure is taken and read with an ion chamber. Initially, no absorber is placed over the chamber, this reading is designated as the 100%. So we take the exposure with the technique that is standard that we have set for this test, and we're going to read it out on the chamber. That's going to be our 100% mark. Then thin sheets of aluminum are added until one measure is obtained below the 50% level. The sheets typically, they can come in 0.1 millimeter, 0.5 millimeter, all the way up to 1 millimeter in different increments, and that can be added. They're typically taped to the collimator, to the housing of the collimator, right where the light would shine, right where the x-rays should be coming out in the primary beam, and they're typically taped up there. The points are graphed and a best fit line is created. The horizontal line is then drawn from the 50% on the y-axis and graphed into the graphed curve. Then the vertical line is dropped from the x-axis to the value, and whatever value that is, that's the half value layer. For a three-phase unit, the half value layer at 80 kVp is about 2.34 millimeters of aluminum. If the unit exceeds minimum requirement, the kVp of the equipment is calibrated using an oscilloscope. Then if still out of range, filtration is added to the tube. So we can add filtration can be added to the tube to adjust what the half value layer is, or it could be taken away, I suppose, too. Also, it can be calibrated with an oscilloscope, which is a piece of electronic testing equipment. And the equipment is retested until it passes the parameters that it should be within the half value layer. We'll go ahead and we'll just look at this here for a second in action. So this is the x-ray tube. It comes through the collimator here, right in the primary beam, and then thin sheets of aluminum are added here as absorbers. Originally there's nothing in the beam, and we just, with the ion chamber, that value is just taken, and that will be the 100% mark, whatever that value happens to be. And then we keep measuring. We'll add a bit, whatever point of aluminum, 0.5 maybe, then we'll take another measurement here, and we'll figure out what percentage that is of the 100%, and we'll keep going until we get values below the 200%. So this is actually a test that was ran on actual equipment, and this 70 kVp was used. So the points were found below the 50% mark throughout the test, and a curve was created, which is this blue curve from all the values given. Then a horizontal line was taken from the 50% to the curve right here. A vertical line was dropped down to the x-axis, and that corresponds to about 2.65. So the half value layer of this machine is 2.65 millimeters aluminum equivalent. And if that's within parameters of what it's set by the physicist and the manufacturer and everything, then this would be acceptable. If it's not, then it would need something would need to be recalibrated, as we talked about with the oscilloscope, or added or taken away filtration of the added filtration. Now let's talk about kVp calibration. kVp is checked by placing various amounts of filtration over an ion chamber. If this sounds a lot like the half value layer process, it's because it is. kVp is extrapolated from the half value layer. When the half value layer is out of calibration, the kVp can be checked by more sophisticated methods, as we talked about, using an oscilloscope or voltage diode instruments. This is what an oscilloscope looks like. It's a piece of electronic testing equipment. Most states are plus or minus 5% is the limit of acceptability. The federal guideline is only plus minus 10%, but most states have the plus minus 5% of acceptability for what the kVp is reading to what it is actually producing. Another parameter test. Now we've talked about MA, we talked about seconds, we talked about kVp. So we have the three parameters that we set at the console. The other main factor, primary factor, is distance. We talk about collimator and the distance. It is essential that the field light control knobs of the collimator and the projected field light accurately indicates the field and location of the actual X-ray beam. So all because the light is shining on a certain area, is the X-ray beam actually exposing that area? That's the question that we need to ask ourselves here, and that we're going to test for. Slippage of the collimator gears or belts and or a mirror that is crooked could be the cause of the misalignment. So the light shines right here. The light shines on a mirror, and that mirror should accurately represent the same path that the X-rays are going to take. So if this mirror is misaligned, or if there's slippage of these gears that open and shut the shutters, the collimator shutters, then there's going to be some misrepresentation of the light to the actual X-ray exposure area. The tube is locked into a 0-degree position, so to test it, and precisely centered to the plate. Then light is opened to the edges of the plate. Each dimension should fall within 2% of the SID from the length and width of the demarcated plate. Okay, so there's a plate that has marks on it. That's all that this means. Okay, and then the light is opened up to the marks. The exposure is taken, so we know that the marks are a very set distance. The exposure is taken, and then the film is measured from there. The image is measured from there, and it should be within 2% of what that measurement should be, of what the light was shining to. That's all it's saying, that the exposed area should be within 2%. So it could be plus or minus the 2% of the marks. That's the acceptable range. Another parameter is the central ray and SID. So we talked about the collimators. We talked about the exposure techniques that we set at the console. Now we'll talk about the central ray. It is indicated by a metal screw or BB embedded in a small plexiglass cylinder. So we use a BB that's in a small plexiglass cylinder, which should fall within 2 concentric circles indicated on the plate. The central ray should fall within 1% of the SID from the indicated light field. Distance indicators may be checked by using a tape measure. So in order to test the actual distance, an actual tape measure can be used. Okay, so if it, especially in digital equipment now, it will say it's at 72 inches or 180 centimeters. Okay, and that will be on the display. Is it actually there? From where the cassette is, not from the board, and or the front of the tube or anything like this, but where the cassette is, where the exposure is actually going to be detected at, to the focal spot. Okay, which is where the X-rays are actually created. That should be within 2%, plus or minus 2% of what the equipment says it is. Okay. This is the central ray tester, indicated by the metal screws. And this may also be the demarcated plate right here with the marks on it. Okay. So in here there would be a BB. This is the cylinder, the plexiglass cylinder. It should fall within 2 concentric rings indicated on the plate. Okay, so there's rings on this plate. It should fall, the BB should be within that for the central ray. If the central ray is off by some degree, it's going to throw it out of those rings. Okay, and this is what the image looks like. So here's the rings right there. After the picture is taken, the BB's right there. It's directly in the center. So this central ray passes. To test the SID, we'll use a tape measure, and then those two tests are completed. Focal spot size and condition. The nominal focal spot size is quoted by the manufacturer. So the manufacturer says this focal spot's 1 millimeter. The manufacturer says this focal spot's 1.2 millimeters. Okay, that's based on the manufacturer. The resulting focal spot size depend on the tube geometry, but also on correct focusing of the electron beam, which is inside the tube from the cathode to the anode. Therefore, manufacturers are allowed considerable leniency in varying from the nominal size. So there's a wide range of acceptability here, is what this is saying. Under 0.8 millimeters can be 50% larger. Can be 50% larger. So 0.8 could be all the way up to 1.2, all the way down to 0.4, I suppose. It says larger. I don't know if that also counts for smaller, but let's just assume only 50% larger. So it could be all the way up to 1.2 millimeters. Greater than the 0.8 can be 40%. On all these other tests, there's 2% for the SID, there's 5% for the reproducibility, and things like that. On here, there's 50%, so that's a much wider range than any of the other tests we looked at so far. Size can be measured with a slick camera. So there's a thing called a slick camera that can measure the size. Focal spot blooming is something that will happen. It's due to the mutual repulsion of the electrons in the space. Inside the tube, we have the cathode and the anode. When the electrons go from the cathode to the anode, they're attracted to the anode, but they're also repulsed, okay, by the other electrons. So they're going to not exactly hit the anode right in the focal spot the whole time, which is what we're testing here, the focal spot size. So the size of where the x-rays are actually being produced is going to grow larger, okay, because of this. This is a thing of physics, okay, of quantum physics at that. This is what the blooming can look like. So the scanner at 70 kVp, scanner, it says scanner, which this may be a CT tube, scanner at 120 kVp, and you can see how at different MA stations, yeah, this is probably a scanner because it's 980 MA. Maybe it's it doesn't matter, but 980 MA compared to 300 MA here, how much larger this focal spot is, okay, because there's so many more electrons here that this blooming becomes a real factor in the appearance or the of the focal spot, okay, of how it's being represented, let's say here. And so on this one, you can see it's this size here, and then it becomes very large at the 900 MA, it looks like here. Okay, so this is focal spot blooming. The more important measurement of focal spot is that of the condition of the focal spot. So how the focal spot looks, you know, how well of a condition is it in, okay, rather than the size. This is done off the baseline measurement. The baseline measurement when the equipment, that means when the equipment is first installed. There's a baseline measurement it's taken, and then it's compared to the test being done currently. This is a picture of the slit camera. Okay, so in here there's little lines. Okay, and this is the focal spot test tool. All right, and this is what the output would look like. All right. And again, this is a diagram of how the focal spot is projected, and really a lesson in umbra and penumbra here, where umbra is the main region and penumbra is the blurriness region due to the object. And the larger the focal spot becomes, the more this blurring occurs, as we can see here. Two different objects, like it's like kidneys or something would be here, maybe that were, or maybe even the lungs would be here on two different sides, and how the blurring can occur the larger the focal spot could be. So that's why this focal spot testing and really the condition of the focal spot is an important aspect. Automatic exposure control. To check repeatedly, 5 exposures should be taken using an ion chamber. So to check the automatic exposure control, you take 5 exposures with and the ion chambers used. The AEC exposures must be repeatable within an accuracy of 10%. Also, linearity should be within 20% between the rooms. So in a facility, if you're testing different rooms, the linearity of the automatic exposure control should be within 20% from room to room. Each exposure should be within 10% accuracy. So if you're exposing the same object again and again, it should take an exposure, as measured by the ion chamber, within the plus minus 10%, okay, every time. Then each room should be within 20%, so there shouldn't be too much of a variance between the rooms. The backup timer is tested by placing 3 sheets of leaded rubber over the cell. So each of the automatic exposure control, there's the cells, there's usually 3 of them, and if there could be 5, there could only be 2. And then they cover up that cell. They take the exposure 5 times over the cell, and the exposure should terminate at 600 mass. So this is a calibrated sheet, okay? And after 600 mass, it should terminate. That may be the set limits of rooms nowadays is a 600 mass, and that can protect the patient from overexposure. And also, which doesn't happen much in DR anymore now, but in film or in CR possibly still, where you have the chest bucky selected instead of the wall. So now you're exposing, and of course that one, since the tube isn't pointed at that one, it's just going to keep exposing because it's never going to terminate the exposure, the AEC. Okay, but it's actually focused at a person, at the patient. So the 600 mass may be the limit of that's set by operating equipment. I'm not quite sure, or that just may be the standard of the 3 sheets of leaded rubber, and it may be it may be calibrated, the 3 sheets of the rubber, where it should be around 600, and the accuracy should be plus minus 10% from exposure to exposure. Monitoring of digital acquisition systems, field uniformity. So digital detectors are all inherently non-uniform. So we're talking about DR now. So we're talking about the DELs, okay? Inherently, they're all non-uniform. Uniformity corrections must be repeated daily to semi-annually. So the daily detector calibrations and things, this could be done by techs, could be done by us. The more higher end and involved ones might be done by like somebody who does the QA, typically with a more weekly test or monthly test, and then the semi-annually test would be done by field service engineers or physicists, okay, to keep to make sure that detector is still within compliance, and also since it's electronic, it can recalibrate itself during these tests too. If a radiopaque artifact is found, a non-uniform detector field may be the cause. So if there's an artifact found in the image, this would be the field uniformity, non-uniform detector field. So there may be something wrong with the detector. To check the plate is to be thoroughly erased, and an exposure is taken with no object in the beam. So this would be like CR. If there's like a ghosting artifact, perhaps you should do a thorough erasure of it, and the resulting image can be scanned for defects. So this really more only applies to DR more so. This applies more to CR, but there's interchangeability. Erasure, thoroughness, and ghosting. So we just kind of talked about this. Inadequate erasure of a CR system can arise. A residual image will still be present. Exposure of the plate with a step wedge, then immediately re-expose the same plate without the object in the beam. Visually examine the second image for any ghosting of the step wedge. So we take a exposure with a step wedge, which can be seen right here. Then we run it, we erase it. It goes through the erasure process. Then we take another exposure with nothing in the field. We visually examine the second image for any ghosting of the step wedge. Can we see the step wedge still in the image? If we can, there's a ghosting issue, possibly, or an erasure issue with CR. In DR, ghosting image lag or memory effect is what it can be called can occur. It can be checked the same way. So we can do the same exact process with this, re-expose it, see if there's still something there. The electrons are trapped in a metastable state and is released slowly over time. So after the exposure is taken and it's sent, usually it could be through a tether, or it could be directly, or it could be through Wi-Fi. The image is sent to in DR, the image is sent to the computer, processed, displayed on the image. We would see the step wedge. It should erase. It should have dumped all that information out. Okay, all those electrons should have dumped out to the read lines. But it's possible that they didn't. So there's still that information stuck there. So now if we take another exposure, that should be just a clean field of uniformity of this noise. Then, and we still see, we can still see the step wedge, we can still see this outline, we can still see some kind of indication of it, then there's something going on with the DR system. The last thing we'll talk about is intrinsic noise and spatial resolution. Intrinsic noise can be checked after a plate is erased and then processed without exposure to any of the X-ray beam. So we thoroughly erase the plate in CR. We don't expose it to anything, any part of the X-ray beam, and then we run it again. And then the image is visually scanned. It should be uniform white snow. There shouldn't be any major inconsistencies in the snow. Okay, there shouldn't be any really dark spots, any really white spots. If there is, there's a problem with the plate in CR or in DR. If we recreate this process, it should just be uniform static. Okay, it should just be uniform background. Okay, but if there's a dark spot, it may be a dead cell, a dead Dell detector element, or it may be something else going on. If there's a whole line of black, it could be the readout lines are there's something wrong with them. The detector may need to be replaced at that point. Spatial resolution can be tested with a wire mesh. A wire mesh is put on the plate, an exposure is made, and the image is visually examined for any distortion or unsharpness. So this would be the spatial resolution. So, okay, so this is the wire mesh right here. This is what it should look like under exposure, where it's just like a grid pattern. This is an issue with the spatial resolution. So in this area, there's some kind of reading. It's either with the plate, it's either with the image display, it could be with the processing. So there could be a lot of things going on here, right? All these things make up the spatial resolution in digital. Okay, digital being CR or DR, radiology. Also, the standard bar test pattern can be exposed, and the line pairs per millimeters can be obtained. So we can find the spatial resolution of the system, make sure it's still within the acceptable limit that it needs to be with the bar pattern test. Okay, and these would be the line pairs per millimeter, and you should be able to see clarity down to a certain amount. And if you can't, it's not within calibration. Something needs to be fixed. Something needs to be changed. This is a summary of the tests in the ranges of acceptability that we talked about in this video, along with how often they're typically performed. There are many more tests which are performed on radiographic equipment. However, it's very common that now that field service engineers or physicists will perform a lot of these tests, it's still beneficial to have an understanding of the common tests that are performed, how they're performed, why they're being performed, and the typical ranges of acceptability that are allowed for the common tests. In the next video, we will go over artifacts and repeat analysis.